In the last video, I showed you how to take this clock module from Ben Eater's Building an 8-Bit Computer on a Breadboard project and build it into an FPGA so that you have less wiring to do. And I demonstrated that using source code from the Alchitry Labs IDE and the Alchitry Labs AU FPGA board. In this video, I want to take the work that was started from that last one and do a little bit of cleanup because I had things scattered out between the top module and the clock module, and to me it didn't make sense, but you know, as you create the stuff, that's kind of the way it turns out. So we're going to go back and make a few modifications and improvements. The first thing that I wanted to do is take some of these button conditioners that I had in the top module and move them into the clock so that you could feed raw signals, dirty signals into the clock, and the clock would just take care of them. So the first thing, let's take the auto manual conditioner and move it over to the clock. Now the auto manual conditioner has got to get wired up into the clock. So let's do that. And that will get wired up to this input as part of the module, right? Like this. There we go. So there's one that's been taken care of. And what is this complaining about here? Auto manual conditioner was never used. Oh, probably because I am referencing the signal as opposed to the conditioner out. So let's take care of that. So here we should be referencing the output from the conditioner. We should be referencing the conditioner first. Like that. Let's see. Let's do, and I'm not even familiar with this IDE. How can you even do a search? Let's see here. Maybe Control F. Not sure. Ah, you can. How about that? So we want to look for this. Ah, great. So we reference it there and nowhere else. Okay, great. So that this signal now, this auto manual signal, which tells us whether we're going to free run the clock or manually step the clock, can be dirty coming into this clock module. And then we have a button conditioner component that we move from the main, from the top module into here. We've wired it up to the input signal coming into the clock module, to the input of the conditioner. And then on the output side of the conditioner, we changed, or on the where we were referencing the raw signal, we're now referencing the output of the debouncer. So that's great. Let's come back and do the same thing to the advanced condition, to the advanced signal. The advanced signal is what you'd use to advance the clock one tick at a time manually. So this one here, let's take this one out and stick it here. And same sort of thing, we want to wire up the input of the button conditioner to the correct signal, which is the advanced signal. Like that. And now wherever it is we're accessing that signal, we instead want to access the output of the conditioner. I believe that's right. And I check periodically as I'm going along here. And of course, I do get some errors. That's interesting. So what is this complaining about? Oh, probably up here somewhere. Oh, of course. So in my main module, I am referencing the conditioners, which don't exist anymore. And so really, these buttons now need to be wired directly to the input of the module, which is what we wanted to do in the first place. So here, instead of the advanced conditioner in, we really want this to be clock. Let's change this. This should be clock dot clock dot advance, and the auto manual should be clock dot. I'm not sure why the tooltips aren't working. That's kind of what's got me a little confused, but that's fine. This should be the auto manual B signal. Yep, just like that. And then, so these references, yeah, so let's move this around because these are the references we just replaced. Let's just move them down here. Take these out. Stick those in. There we go. And instead, wire up manual clock advance button. That's just it. We're not wiring it up to the debouncer anymore. We're just wiring it up directly to the module. Yeah, just like that. Let's run the check again and see if it's happy. No, it's not happy. What else have I missed? Oh, so right, our LED was a combination of these two signals of both the clock as well as the manual advanced indicator, which we're going to move the manual advanced indicator, or really we're going to move this logic, I think, into the module as well, because it makes sense that the clock module not only gives you the output of the clock that you presumably would wire up to your breadboard computer, but it would also provide an LED signal. Like when you manually advance it, if the tick is too small, and of course it will be because it's coming from the FPGA, you still want some visual feedback that your manual advance worked correctly. So I created this little bit of logic here to provide a delay on the LED so that, you know, when it advances, it lights for at least a little bit of time. Now this signal is, we just need to reference the state of the auto manual signal, which let's just reference it directly. It's not the condition signal, but that's okay because by the time we get down here, I think the signal should already be settled. Let's just see if that's going to work. I'm not quite sure. So the auto manual signal is going to be outputted here on this dip switch. And I've also thought about creating signals for these dip switches so that these things can be named something better. Like, for example, let's just try this because I'm not sure. And I'm new to this stuff too. I'm not sure if this is going to work. Let's create a signal called I don't know, auto manual B for bar, because manual is low, active low, switch. And then what we'll do is we want to initialize it. So let's just initialize it here. So auto manual B switch is equal to, we want to set it equal to the right dip switch. It's this one here. Seems to like it. You know, that way we can alias these things, and maybe you can just initialize it up here. I don't know. Let me try that. Can you do that? Let's see here. No, evidently you cannot. Module IO. Oh, it's wanting a module or something. Okay, that's fine. So let's give nice name to auto manual switch. Perfect. Now, wherever it is I'm accessing dip 00, I want to use this nice name instead. Code's getting easier and easier to read, which is nice. Perfect. And I will make a change to the rest of it, probably off camera, so you don't see me typing all that. Let me just design rule check it. Great, no errors now. So that must be good. So I'm going to go ahead. I like to do these things a little bit at a time just to make sure that I don't break. So let me go ahead and compile this. Okay, project finished building. Let's load it. Looks like it's done. Let me blow this up a little bit here. There we go. And let's double check it to see if it works. Right, so the first switch, again, is the free running clock, the auto clock. That makes sense. Second switch is the halt. It halts. And then does its single step. Yep, still single step. So looks to me like it's all working. That's great. So I made a few more changes off camera while the project was building. Basically mapped the IO button to a nice name here because I can't remember the array indexes to all these things. I like the nice names. It makes the code a lot cleaner so that you can understand what's going on better. So the next thing that we want to do is let's look at this here. So this manual advanced indicator. So we want to move that, I think, into the clock module so that the clock module just provides to the user another signal that they can hook up to an LED if they want to. So let's go back to the clock module. Let me get this down here because it's too big. So we want to add another signal. Let's call this signal, let's put the outputs together. Let's call this output. Let's see, what do we want to call it? We want to call it clock indicator. How about? Signal to give clock state. Right, because we're not intending for this to be the signal that you would hook up to other circuitry for the clock output. We're intending for this signal to be an indicator that you'd hook up to an LED or something like that. Right. So back on the top, we have a flip-flop that stores the state of the indicator. So let's steal this. We're gonna yank this stuff over from the main module and stick it in the clock. And I'd like for my comments to line up. I guess it's just a little bit of OCD, but that's okay. Bear with me. All right. So we've pulled it over. Now there should be a bunch of complaints down here. Right. So this stuff, and maybe we can just get lucky and copy it over. And we need, well, I can see one thing that we're already going to need, this advanced hold counter. That's the counter that is holding the LED on for a period of time after you've manually advanced the clock. And obviously we're going to need that in the clock module as well. That's okay. Let's take this stuff. And we will stick it in the always block. And just a comment on where to stick it. Let me digress for a second because I'm still sort of trying to get this straight in my head. You know, an always block, it's wrong to think of an always block as a procedure, as a function. It's likened to that when you read the book, the documentation. But the reality is, in an FPGA, this is not a procedural function. This is not a CPU that's executing instructions one by one, you know, down the function. This is a think of this better as a design where all of these things can simultaneously occur. Now, it's not practically speaking that way because when you set a signal, the latest signal that is hit in the always block is the signal state that will occur. So, you know, it's not unlike procedural programming because, you know, if you set a variable up at the top and you set a variable at the same variable at the bottom, then the variable state is whatever's at the bottom. So, you know, it sort of works that way here, but it's not true to think that that variable went through two state changes in this design. It's basically as if the first state or variable setting actually never occurred in the first place. Anyway, that's a bit of a digression. I'm going to stick this code, well, let's just Let's just stick it up here. That's probably the wrong place. Right, so we need our advanced hold counter. That's fine. Let's go snag it from our top module, which is nice because I don't really want it in here anyway. And we're not going to wire it up to the reset signal because we control the resetting of it ourselves. And this is actually where we're controlling it. And it's in the always block because the typical state for the reset for this counter is to not be reset. So let's set this up here. Right, so our out signal is an output only, which makes sense. So what we really want here in this interrogation is, we want to know what the value of out is, but that is being held in this signal variable that I wired up down here. Right, so this is where the order does matter. So we've defined our clock state down here. Let's pull it up here. And I changed resolutions from last video. Let's pull some of these lines down so they're not overflowing and easier to read. That's a little better, I think. All right, so we've defined our clock state. We've pulled the interrogation of the clock here so that we can start our advanced hold counter in case we're in manual mode. I think that all makes sense. Right, so this code down here to figure out what the indicator should be, it shouldn't go here. It needs to go in the clock. So let's yank that out as well. We're going to take that out here. We're going to stick it in the clock, and we just need to wire it up to the correct signal, which in this case is the clock indicator. So I'm just going to do, I'm just going to stick it here. Clock indicator is equal to this stuff. Now, of course, it's not quite that stuff because the signal names have changed. So our clock out is actually clock state. And our auto manual B switch, that is our conditioner now. Remember, we've changed it. Want it to be the output. And again, here, this signal is the inverse of that. Right, so our clock indicator, which is what we're going to hook to an LED, is whatever our clock state is, ANDed with the auto manual switch. So auto is high. Or it is the manual advanced indicator state, whatever the state we want that LED to be in, ANDed with the inverse of the auto manual conditioner. So we want to look at the manual condition here. So it ORs these two together, and that gives you the state of the clock indicator LED. That makes perfect sense. So let's do a design rule check. And I have some more complaints. Let's see what it's complaining about. An AU top. Line 95. Mismatch parenthesis. Do I have a missing? I'm not seeing line 95, column 2 on AU top. What am I missing here? AU top. Oh, of course. So I need to now fill the LED with the signal from the clock. Let's see here. Clock indicator. Like that. No errors detected. Great. Let's see if I think this is everything we want. Pull this down. Yeah, I think so. Let's do the build. Okay, the build finished. Let's check it out. Does the free running clock work? Appears to. When I click the button, get my hand out of the way, click the button, manual advanced button doesn't do anything in auto. Put it in manual mode, and we get a button and we get a visual signal, which is good. And our halt still seems to work. And the halt is also working on the manual mode. Yep, all our changes appear to be good. So the next thing that I want to do here is back in the main module, we have a period variable. I keep saying variable. I'm not sure that's the right word in FPGA land. But in any case, we have a period defined of 29 bits here, which is to provide the delay to our clock module's clock so that it doesn't run at 100 megahertz, which is what the clock on the FPGA runs at. The back in Ben's design, actually, if we go back here, you can remember in Ben's design, this chip here, this is the 555 timer. Actually, all three of these are 555s. These two timers are providing debouncing capability. This timer is the actual clock to this clock module. Well, in our FPGA, it already has a built-in clock itself. Now, I guess if we really wanted to be purists about this project, we'd maybe build our own clock and pump the clock signal into the FPGA's fabric, hooking up the other logic circuits that we have been in the process of doing for the clock. But that just seems like a lot of work for really no good reason, in my opinion. So in any case, we do, though, want to provide a scaled down mechanism to scale the 100 megahertz clock down to something that we'd more likely want to run as part of this breadboard computer project. So that's what this value is providing. You give it to the clock module, and then it uses that to scale down the 100 megahertz clock. However, I and the project have basically just hard-coded a value here, which provides a 1 second period, but we want the user to be able to dial a potentiometer, perhaps, or maybe just click some buttons to speed up or slow the clock down. Since I don't have a potentiometer, let's see here. Since I do not have a potentiometer on this board for now, and I'm not hooking up to a breadboard yet. I will be, but I don't have it yet. It probably just makes sense to just click when you click the button, you know, an up button and a down button, that the speed of the clock would speed up or slow down. So how do we do that? Well, we need to provide some inputs. So let's provide some inputs. Faster. Speed up the auto clock. And slower. Now, I think the way that I really ultimately want to do this is probably with a potentiometer. There's just something more viscerally appealing about twisting a knob to do this than it is to push a button. But the book that I bought to learn this stuff is this book right here, The Learning FPGAs by Justin Rajewski. It's a good book. I recommend buying it. That book talks about how to program the Mojo board, which is an earlier version to this Alchitry IO board. And on the Mojo board, there is a Arduino that provides analog inputs, and the book talks about how to access it and so forth. However, the Alchitry Au board has its own analog input mechanism. I haven't explored how to use it, how to address it yet, so that's probably the way I'd want to go. But for now, what I know how to use are the digital inputs, so let's go with that. So we want to slow down the auto clock. And I stuck my signals in the clock module. It's not the right place. We want these to be user interface signals. So let me back this back out. Go back over here. We want faster, slower. So let's just create some signals then. Faster button. And a slower button. And I confused myself because we already have this period variable on the clock module, which tells the clock what the scale factor is going to be to scale the clock down. We just need a way to provide a user interface to the clock module to provide that value. So give nice to button speeding up clock. Great. So let's assign some buttons to those names. Where'd it go? Right here. And, you know, I don't know which button matches to what yet, so let's just, I'm sure it's documented somewhere, but I don't have it handy. So let's just assign some and we'll see what happens. Two. Okay. Now what we need is a way to hold the state of the value that we're going to use to assign to period, because we don't have that here. So let's create ourselves a D flip-flop. I think, yeah, let's see. Yeah, a D flip-flop. And let's just call this current period. Now it needs to be the same width as the period that we've defined over here. So 29 bits. To store state of current clock period scalar. Current clock period scalar. Okay, that works. Now, we want the what do we want? Well, it needs to have a default value. So let's give it a default value. And I don't know what it needs to be. Let's let's think about this. We want to bit shift the 1 because the way this is going to work is when you click the faster button and the slower button, we're gonna code this up to basically bit shift a 1 either left or right. But we want to start this up at a reasonably, not too fast, not too slow speed. So let's bit shift a 1. I don't know, 20, 24 times. Let's see what that does. And of course that needs to be data, the D signal. Okay. And now we need some switch conditioners because we've got some buttons that we need to debounce. So let's add those in. And I'm lazy because I don't want to retype the stuff. So let's just define ourselves from here, some button conditioners. We want to call this the faster conditioner. All right, so now we have 2 button conditioners. Let's wire those button conditioners up. So the faster conditioner in is going to be the faster button, which we and of course I have not wired up the faster button. Oh yeah, I guess I did there already. A little bit more indirection maybe than we might otherwise need, but that's okay because I don't like referencing the arrays, or remembering to reference the arrays, because I'll always forget. slower button. Great. So now we've got some conditioners. So now we need to do is write some code that will simply bit shift those conditioners over. So that's pretty simple. If the faster conditioner, faster conditioner out, if that's high, then we want to bit shift the current period so we want to set D equal to Q bit shifted over. Yeah, that's right. I confused myself for a second. Yeah, so we want to bit shift the value that's in Q of the current period, want to bit shift it to the left by 1 to, no, actually that's not right. Faster. So we want I thought that's why I was confusing myself. Faster conditioner, actually we want to bit shift it the other way, that way. Because the smaller that the current period value is, the faster that the clock is going to clock. Okay, that's why I was confusing myself. All right, likewise, if slower out, then we want to go the other way. Right, because move it to the left, that's going to create a bigger period number, and that will scale the clock slower. Okay. What we need to do is also put some edge condition checks around this, because what happens if the, for example, current period bit shifts. What if we have a 1 at the very end and we shift the 1 off? Well, then it's going to flip to all zeros, and we surely don't want to do that because the user will get confused. So let's put a check here. If actually, let's just put an AND condition up here. So if our slower conditioner is tripped and our slower conditioner, the bit of our slower conditioner, how big is this thing? Sorry, current period. That's what I was looking at. Current period, not conditioner. Right. That's why I was confusing myself. So the current period, we need to check the top bit, and that top bit is 28. So if the 28th bit is set, actually, if it's not set, and it's the Q value, right? So if the output of the current period 28th bit is not set, and our slower conditioner says to go slower, then we'll bit shift. Otherwise, we just don't do anything. Likewise, we can check that up here. If the current period actually, you know what? It doesn't matter. They're all going to be zeros anyway, so it's no use actually continuing to check. If you just keep shifting zeros over, it's just going to keep being 0, and that's fine. Now that's going to imply that the clock can run potentially at up to 100 megahertz, but we'll see if this breadboard computer can actually run that fast, I guess. Okay, so let's do a design rule check. Oh, no. So we need to assign period. That's the whole point of this exercise, is that current period dot Q needs to be assigned to the clock period. Okay. Now I think maybe we have everything. Okay. Design rule check passed. So yeah, I think those are the changes that we need to make. Let's do the build. The build is done. Let's turn on the board so you can see that, and let's load it. All right, it's been loaded. Now let's see if we broke anything. Well, the light's flashing faster, so that's a sign that some good change has been made. I off camera looked up what the order of the push buttons were. Button 0 is up. We knew that because that's the manual advance. Button 1 is center and button 2 is down. And that's not the way I'd probably leave it, but that's the way it is. So so button 1 is the faster button. So let me click that and see if we get a faster light. No, we do not. We get no light. We get a long delay before it starts up again. So obviously something is not right. I'm going to go figure it out. Okay, I looked into the code and thought about it for a while and found some bugs. Still not completely working, but I think I actually figured out what the last bug is, so I'll fix it while you're able to watch. Just talking about a couple of bugs, I changed my default setting to be conditional because I realized that it was setting it constantly, so that definitely would not be correct. So we only want the default period set when the default period's all zeros. Now I think this probably should just be looking at the reset signal, but this does work for now, so I'm just going to leave it that alone. The second bug that I thought about was, and this wasn't still not the complete problem, but I know it will be, is when we're bit shifting to the right, we don't want to bit shift the 1 all the way off, leaving no period. So I added a check to look at the last bit, and if we are at the last bit, we don't want to completely bit shift that 1 off. So I made that change. Finally, in the clock, I made a change here. What did I do? Well, maybe I didn't. Well, so let's just go look at what the current state of those changes are doing. And I'm going to hit the reset switch. Okay, so it flashes like it was doing before, a little faster, showing that my default is working. Now, when I hit I think this is the speed up button, you'll notice the light goes out. Actually, if you look really carefully, and let me see if I can shield the light a little bit. Yeah, so you can see there is a little bit of a green light lit. And what that's telling me is that the board is flicking that light really, really, really fast. Or really, it's just not providing any voltage. When I hit the slow button, you can see now that it's blinking really, 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 really slowly, which almost looks like it's blinking at the slowest speed that it's going to blink at. So why is it behaving that way? Well, it occurred to me, I started to think about, well, do I not understand bit shifting correctly? What is it about this code that's not working right? Well, what's not working right about it is that out, for the duration that you hold the button down, out is asserted. And so very rapidly the FPGA is bit shifting this all the way to one side or all the way to the other. What we actually need is an edge detector hooked up to the conditioner to just edge detect when we get a rising edge on the button. So let's do that. I have an edge detector over here. I'm going to copy it because I want the declaration. I don't have to retype it because I'm lazy. And an edge detector, yeah, it doesn't have or need a reset signal. So we want our faster, we're going to call it faster edge. And we want it to trigger on the rise. We need a slower edge detector, again, to catch on the rise. And we need to hook those up. So our faster edge detector in is going to be equal to faster conditioner out. And we need to hook up the slower version. Great. Now, instead of looking at the button conditioner, we need to look at the edge detector. So that would be looking at edge, as would this one. Now, let's check the design. I get no errors. Let's build it. Okay, project's built. Let's load it and see if the fixes worked. All right, so the light's flashing. Let me pull this bigger so we can see it. Light's flashing. Let's speed it up. Oh, look at that. And let's slow it down. Great. That is sweet. And, since we're moving powers of 2, maybe that's just not exactly what we want. But, we've proven that the clock module works the way we wanted to, and we were able to easily hook up a quick user interface. In the next video, I think what I want to do is pull this I/O module off of it and actually hook this thing up to a breadboard so that we can start building the CPU components out on it. And maybe, and the nice thing is we can switch it back and forth so that, we can do a little development with the I/O board in it and then plug it back into the breadboard and look at the other user interface components that we want that will make it look more like what Ben Eater's breadboard project. Thanks for watching.